Brought to you by Thomas Allgaier and Frennis, this edition highlights key LinkedIn posts on electrification and battery technology in weeks 12 and 13. Frennis is a B2B market research company that supports automotive suppliers with building feature-by-feature competitive intelligence that shows exactly how their product stacks up against the competition. You can find more info in the description.
All right, welcome everyone to today's deep dive.
Yeah, welcome. And, I want you to just imagine something for a second. Imagine buying a brand new electric delivery truck, right? You calculate your operational savings down to the penny, you pull up to your facility, and then
You realize you can't actually turn the chargers on.
Exactly. Because your local power grid just won't let you plug it in. And that is exactly the kind of reality check we're exploring today.
Right, because we are cutting way past all that theoretical hype of electrification today and slamming right into operational reality.
Yeah, so we've been curating these top insights from mobility professionals over the last 2 weeks, specifically calendar weeks 12 and 13. And our mission here is to unpack the smartest strategies that are currently circulating in the industry.
Because the conversation, honestly, it's fundamentally shifted.
Yeah.
When you look at the posts from these past couple of weeks, nobody is really debating whether the transition is happening anymore.
No, not at all.
The entire focus for professionals right now is just on the how. How do we build this? How do we pay for it?
Right.
And really, most importantly, how do we integrate these megawatt scale power demands into systems that were, built decades ago for just a fraction of this load?
So let's start right there at that physical bottleneck, because I think a lot of people outside the weeds of this industry, they just assume EV charging is like a hardware procurement issue.
Oh, absolutely. They think you just buy a charger, you bolt it to the concrete, and boom, problem solved.
Right. But looking at a really great insight from Tom van Grinsven recently, that is entirely the wrong target. The public fast charging stations, they actually aren't where the rollouts are failing.
No, they're failing where the cars actually sleep.
Yeah.
Tom points out that the real graveyard for EV rollouts is at the home and the workplace. Because, a company might breeze through a pilot program with, say, 5 cars, right?
Sure, 5 is easy.
But the second they try to electrify a fleet of 100 employee vehicles, the operational complexity just totally explodes.
You have employees taking vehicles home who need a system for fair energy reimbursement. You have workplace parking lots with these really strict electrical switchboard limits.
Right. And suddenly your finance department is throwing up red flags everywhere.
Exactly. Because they are looking at this massive unforeseen capital expenditure just to upgrade the building's electrical panel.
Yeah.
It's like, I was thinking about this, it's like buying this high-end commercial espresso machine for your office, but you completely forget to check if you have plumbing.
Yeah. Or a strong enough electrical circuit to even turn the thing on.
Exactly. So, wait, if a company is bleeding cash trying to upgrade switchboards just to give employees a place to plug in, what's the alternative here? Do they just halt the rollout entirely?
Well, no. This is where Tom introduces the concept of charging as a service, or CLIMP. So instead of the company buying all the hardware and acting as their own utility company,
Which they don't want to do.
Right. They shift the entire burden to an operational expense. He uses what he calls the 5C CAS scorecard to evaluate if a project is actually going to survive.
Okay, 5C, what are the Cs?
So you have to look at CapEx avoided, tracking consumption for fair reimbursement, managing the physical constraints of the site, establishing confidence through guaranteed uptime, and proving it can scale from 10 chargers to 1,000.
Wow. Okay, so if you don't map out those 5 Cs before you break ground, you just hit a financial wall.
You really do.
Okay, but let's be real for a second. If the physical constraints of a workplace parking lot are that severe, why not just bypass the switchboard problem entirely? Why not just install 1 or 2 of those ultra-fast DC chargers in the lot and have employees just rotate their cars throughout the day like a regular gas station?
So why do we keep throwing fast chargers at the problem? It's a logical question, but it fundamentally misunderstands how electric vehicle batteries actually work.
Oh, really?
Yeah, and Maxime Leguillot shared some brilliant data to answer exactly why we shouldn't do that. You're basically trying to apply a highway solution to a parking problem.
Right.
Maxime's core rule is that charging power must match parking duration. DC fast chargers, the massive 50 to 350 kilowatt units, those are designed purely for urgent trips.
So they're for the highway, not the office park.
Exactly. AC chargers, which are much slower, trickling in at 7 to 22 kilowatts, those are for everyday parking. When a car sits at an office for 8 hours, throwing DC power at it is not just inefficient, it's actually destructive.
Wait, destructive how? Like, are we talking about physical damage to the vehicle?
Yes, specifically to the cell chemistry. Maxime highlighted this GeoTab study that analyzed over 22,000 EVs.
That's a huge sample size.
It is. And it found that, on average, batteries degrade about 2.3% per year. But the mechanism behind that degradation is heavily influenced by how you charge the car.
Okay, so what's the split?
Well, vehicles that primarily use slow AC charging, they only degrade about 1.5% a year.
That's pretty manageable.
But vehicles subjected to frequent high-power DC charging, their degradation spikes up to 3% annually.
Wow. So what is actually happening inside the battery when you plug into a fast charger versus a slow one, like mechanically?
It really comes down to heat and electrochemical stress. When you push massive amounts of direct current into a battery, you are literally forcing lithium ions across the separator at a really violent rate.
Ouch.
Yeah, and that generates immense internal heat, which degrades the chemical structure of the cell over time.
So from a hardware longevity standpoint, you definitely want AC for that daily dwell time.
100%. Plus, Maxine points out that DC charging hardware and the associated energy tariffs can cost like 15 to 20% more per kilowatt hour anyway.
All right, so AC charging protects the battery chemistry and saves money. But that brings us right back to the macro problem, doesn't it? You still need to pull all that electricity from the local grid.
You do.
And I saw Mikko Sumala had a really blunt assessment of this. He noted that local grid constraints kill more projects than lack of budget, lack of planning permission, or lack of customer demand combined.
It's the #1 killer.
Yeah. So if the utility says your building doesn't have the capacity, what do? Are you just stuck waiting 5 years for the utility to run a new transmission line?
Not if you engineer your way around the bottleneck. Mikko outlined 4 practical workarounds for developers who are basically paralyzed by these grid limits.
Okay, let's hear them.
First, you can install battery energy storage systems, so BAS. You trickle charge a stationary battery slowly overnight when power is cheap, and then dunk that power into the cars during the day.
Oh, nice. So you're completely decoupling your charging spikes from the grid's capacity.
Exactly.
Yeah.
You're buffering it.
That makes total sense.
Okay.
What are the other 3?
Second is dynamic load management. Third is using multiple smaller grid connections instead of waiting for one massive commercial hookup.
Right.
And fourth is phased deployment. So building only what the grid can handle today, but designing the conduit so you can scale it later.
I really want to drill down on that second one, dynamic load management, because I hear that term constantly in the industry. But how does that actually work in practice?
Okay, so imagine a smart electrical panel that acts as a traffic cop for your entire building. Instead of assuming all 50 chargers in the parking lot are going to draw 100% power simultaneously, the software monitors the real-time energy draw of the actual office building.
Okay, so it sees what the building is doing.
Right. So if it's a really hot afternoon and the building's massive air conditioning units kick on, the software instantly throttles down the power going out to the parking lot.
Oh, wow.
Yeah, the cars charge a little slower for maybe an hour, but you never trip the main breaker, which means you don't need to pay the utility millions to upgrade your connection.
That's brilliant. It's essentially tricking the grid into thinking you have a smaller footprint than you actually do just through software orchestration.
Exactly.
And that reality of having to creatively engineer around these massive physical limitations, that was echoed in a post we saw by Gelberg Rodriguez. He was talking about the first Megawatt Charging System sessions out in California.
Oh, yeah, the MCS sessions.
Yeah, and they are literally trenching the concrete and laying massive wire in real time while the actual technological standards are still being debated by the automakers.
And that right there is the defining characteristic of mobility infrastructure right now. You just have to build complex physical systems under extreme uncertainty.
Because there are no finalized cut sheets.
No, there aren't. And as Gelberg observed, if you wait for the technology to be perfectly standardized before you pour the concrete, you're going to be half a decade behind the market.
Right. So we are laying massive cables in the dark, we're tweaking software to throttle loads, and fighting finance over capital expenditures. But let's look at what happens when all that heavy lifting is actually done, right? And a driver actually pulls up to a public plug.
Which is a whole other headache.
Because from the insights we're seeing, the hardware is only half the battle here. If the user experience is broken, this entire multi-billion-dollar infrastructure effort just stalls out.
It does. Seamlessly transitioning here, the software and UX layer is currently the ultimate friction point for mass adoption.
Yeah, Bradford Chris had a really fascinating take on this recently regarding Tesla opening up its supercharger network to non-Tesla vehicles.
Which is a huge deal.
On paper, it sounds like a massive win for everyone. I mean, Tesla has the most reliable hardware and the highest uptime in the industry. But Bradford pointed out that for a non-Tesla driver, the experience is a UX nightmare.
Oh, completely.
He shared a story about an EV native driver, like someone who actually knows this industry inside and out, getting completely stranded.
And why? Because the digital and physical handshakes are fundamentally misaligned. Tesla designed this beautiful, seamless, closed-loop system, right? The car, the charger, and the billing software were all built by the same engineers to speak the exact same language.
You just plug it in, and it works.
Right, but opening that up introduces massive cognitive overload.
Yeah, Bradford mentioned that the serial numbers on the physical stalls didn't even match what the app was showing, and then the physical adapter required this bizarre sequence of button presses and pulls that felt like a secret handshake.
Yeah, secret handshake, you have to guess.
And the digital routing was totally fragmented. I mean, imagine you, the listener, right?
Yeah.
Imagine your very first road trip in a new EV. You pull up with a depleted battery, and you can't get the charger to initiate because you don't know the trick to seating the adapter.
Those are exactly the kinds of negative experiences that end up as dinner party horror stories.
Right.
They destroy adoption.
Exactly.
But the friction isn't just digital or physical, it's financial. Matthias Speicher brought up a brilliant point about how current pricing models are actually alienating drivers.
Alienating them how?
He specifically called out charging subscriptions. He argues they don't build brand loyalty at all. They are essentially, in his words, penalty avoidance traps.
Penalty avoidance. Break that down for me. Why would someone subscribe if they aren't getting actual value?
Well, it comes down to how charge point operators, the CPOs, handle their massive fixed costs. To distribute their financial risk, they really want guaranteed monthly recurring revenue. So they push subscriptions.
Right. Everyone loves a subscription model.
But to force drivers into those subscriptions, they set the base ad hoc charging price punishingly high. So from the driver's perspective, you aren't subscribing because the app is great or the stations are super premium. You're subscribing simply to avoid getting ripped off at the terminal if you just swipe a credit card.
Wow.
And Matthias rightly points out that building a business model on customer resentment does not scale.
It creates subscription fatigue instantly. I mean, you literally need a spreadsheet and 3 different apps just to drive across the country without going bankrupt.
Yeah.
But regulators are finally stepping in. Jens Romer posted about a major enforcement shift in Germany regarding the AFIR pricing transparency rules.
Yes. AFI dictates that pricing must be clearly and transparently displayed to the consumer before a session even begins.
Which seems like common sense.
It does, but for a long time, there were no real teeth to the regulation. But Jens noted that Germany just closed that loophole, introducing a €100,000 fine for CPOs who violate these transparency rules.
Wow, €100,000 per violation is a serious stick. But how does simply displaying the price solve the deeper issue of getting ripped off?
Because it exposes the hidden roaming markups. Currently, a driver might use a third-party mobility service provider app to activate a charger.
Right.
The physical station might have a public wholesale price of, say, 49 cents per kilowatt hour. But the app acts as a middleman and bills the driver 71 cents.
That markup is brutal.
By forcing holistic public pricing architecture right at the terminal, regulators are shifting the power dynamics. Drivers can finally see the gap between the base cost of the energy and the massive markup applied by the software layer.
And to give you, the listener, an idea of just how wild these baseline pricing disparities are right now, Nikki Donadio shared a statistic that is genuinely shocking.
Oh, this one is crazy.
Fast charging an EV in the UK is currently hovering around 82 cents per kilowatt hour. In Finland, it's 38 cents.
It is more than double the price for the exact same physical utility.
At 82 cents, you are basically paying diesel money to run an EV, which completely shatters the economic incentive for the average consumer to even make the switch.
It does. And, if 82 cents per kilowatt hour makes a daily commuter wince, consider the impact on a massive commercial logistics company.
Oh, man.
Yeah, if we want to talk about operational costs and diesel money, we really have to pivot to the heavy-duty sector.
Let's do it, because this is where the scale of the challenge really comes into focus. Johannes Matthies shared a breakdown of European road energy usage. Heavy commercial trucks make up a tiny fraction of the vehicles on the road, like just 6.6% of the fleet.
Just 6.6%.
But they consume a staggering 47% of the total energy.
It's an incredible disproportion. Just over 6% of the vehicles are burning nearly half the fuel. The energy throughput required to move 40 tons of cargo at highway speeds is just astronomical compared to a standard delivery van.
So here's my question. If we just established that public electricity can be incredibly expensive, how do the economics of electrifying a massive energy-hungry semi-truck actually pencil out? Doesn't the cost of electricity wipe out the business case for the fleet operator entirely?
See, you would think so, but it doesn't, because of the sheer mechanical efficiency of the electric drivetrain.
Okay, explain that.
Frederick Zohm shared the results of a real-world test that perfectly illustrates this. They took a Neuen ETGX electric truck and ran it on a standard 343-kilometer route in Bavaria. And they ran it directly against a highly optimized diesel counterpart.
Head to head.
Head to head. The electric truck completed the route using just 66 euros and 80 cents worth of energy. The diesel truck cost 226 euros.
Wait. 66 euros compared to 226. Even with commercial electricity rates, how is the gap that wide?
Because a combustion engine loses the vast majority of its energy to heat and friction. Only about 30 to 40% of the energy in a gallon of diesel actually turns the wheels.
Right.
But an electric motor is over 90% efficient. Almost every electron goes into forward momentum. So even if the electricity isn't exactly cheap, the mechanical efficiency is so vastly superior that the total cost of ownership, the TCO, heavily favors the electric truck.
So you save so much on daily operational costs that you rapidly pay back the higher upfront purchase price of the vehicle itself. And governments are definitely waking up to that leverage point. We saw posts from Stephen George and Jason Delvard discussing this massive new policy in the UK, a £1 billion package aimed directly at commercial fleets.
This is huge.
It really is. It offers up to £81,000 off the purchase of a heavy truck, but more importantly, it covers up to 70% of the funding for depot charging infrastructure.
Which is the exact right target. Because if those heavy trucks use the most energy, and they park predictably overnight in private depots, subsidizing the depot.
So what do? Because if they can't charge at a depot, and they can't charge at home, they are forced to rely on the public charging network.
Yep.
And as we literally just discussed, the public network is fraught with fragmented UX, broken hardware, and incredibly high prices, sometimes hitting that 82 cents a kilowatt hour mark.
It's a dual penalty. It drains the company's operational budget, but worse, it destroys worker productivity.
Time is money.
Right. If an electrician has to spend 4 hours a week hunting for a working curbside charger and waiting for the battery to fill, that is 4 hours of lost revenue-generating labor. Paul basically argues that until policy addresses real-world curbside solutions for van drivers, we're only solving half the commercial puzzle.
Yeah, that's a massive blind spot. So to solve for these commercial heavyweights, whether it's a depot truck or a curbside van, we need vehicles that can store massive amounts of energy, charge efficiently, and survive a grueling daily cycle.
Which means we need to look under the floorboards at the batteries themselves.
Exactly. And Manja Mikic posted this really brilliant retrospective on the rise of LFP batteries, lithium iron phosphate.
Oh, this is a classic case study in how an entire industry's engineering consensus can get it completely wrong.
Totally.
Back in 2020, the European battery industry was singularly obsessed with NMC chemistry, nickel, manganese, cobalt. NMC has high energy density, meaning you get more range per pound of battery.
Right, which sounds like the most important thing.
And because of that one metric, European engineers largely dismissed LFP chemistry as inferior. They thought it was cheap and heavy.
But wait, Europe has some of the strictest automotive engineering standards in the world. How did an entire continent miss the potential of LFP? Like, what metric were they blinded by?
They were blinded by the spreadsheet metric of energy density at the single cell level. Namanja pointed out that while NMC won on density, LFP was vastly superior in almost every other holistic category, had a significantly longer cycle life, meaning it could be charged and discharged thousands more times before degrading.
Which is exactly what a commercial fleet needs.
Exactly. It also lacked volatile, expensive metals like cobalt, making the supply chain cheaper and more secure. And crucially, it was far more thermally stable. It is much, much harder to trigger a fire in an LFP battery.
But how did they overcome the density issue? Because LFP is fundamentally heavier. If you put it in a car, wouldn't you lose a massive amount of range?
You would if you didn't change the architecture of the pack itself. Because LFP is so thermally stable, engineers didn't need to surround the cells with heavy, bulky, protective modules like they do with NMC.
Yo, I see.
They pioneered cell-to-pack technology. Instead of putting cells inside modules and modules inside a pack, which wastes a ton of physical space, they packed the raw LFP cells tightly together directly into the frame.
That is so smart.
That spatial efficiency recovered a huge amount of the energy density gap. And today, LFP dominates over 60% of the global market, because competitors looked at the holistic system value while Europe was just fixated on a single parameter.
That's wild. And speaking of that safety margin you mentioned, Neza Lipsina made a point that really stuck with me. She reviews battery safety concepts, and she noted that battery failures don't just happen randomly on the highway. The spark is essentially lit years earlier, at the design stage.
Because hardware engineers often aren't asked the right questions. She points out that a battery system can pass every single regulatory test in the lab and still fail catastrophically in the real world.
Right. Tests are neatly defined parameters. Reality is messy.
Exactly. If engineers don't ask the worst-case scenario questions during the initial architectural design phase, like, how will this pack react to a localized short circuit while parked over really hot asphalt, they bake hidden vulnerabilities directly into the hardware.
It's all about how these systems integrate into the unpredictable real world. And perhaps the most radical real-world integration happening right now is bidirectional charging.
Oh, absolutely.
Christian Zamet highlighted that this is not just a neat party trick where your car can keep your fridge running during a blackout. It is a fundamental shift in economic value.
Exactly. With bidirectional charging, EVs cease to be just modes of transportation, right? They become mobile energy assets.
Yeah.
Think about it. You have a massive, highly durable LFP battery just sitting in your driveway. It can draw power from the grid when wind and solar make electricity cheap and push power back into your home, or sell it back to the grid when demand peaks and prices spike.
But Christian points out this creates a massive strategic battle. The profit pool is moving up the stack.
Right, from the physical electrons to the algorithms managing the charging to the customer interface. And the winner of that value isn't necessarily going to be the automaker who bends the sheet metal.
No, the winner will be the aggregator, the software platform that controls the orchestration of that energy. If automakers don't figure out the software layer, they're going to be relegated to providing low-margin hardware, while utilities and software companies capture all the recurring energy revenue.
Which brings us to a fascinating macroeconomic driver of this entire transition.
Yeah.
And before we dive into this final point, it is crucial to state clearly for you, the listener, that we are not taking a political stance here.
Yes, absolutely. We are completely impartial here.
We are simply reporting an observation made by Aurélien de Meaux and Remco Samuels regarding how geopolitical events are actively reshaping political support for electrification.
Right. Because Aurélien and Remco noted that historically, EV adoption was largely viewed through a partisan lens. It was championed as a green climate initiative, which, often alienated conservative policymakers.
Right. But the ongoing conflict in the Middle East and tensions with Iran are fundamentally shifting that narrative.
Yeah.
We're observing conservative politicians pivoting to actively support EV adoption, not for environmental reasons, but as a matter of national security and energy independence.
Wow, that's a massive framing shift.
It really is. When a country's transport sector is deeply dependent on imported oil, any geopolitical shock immediately destabilizes the local economy.
Sure.
But if you electrify the transport sector and run it on domestically generated power, whether that's solar, wind, or nuclear, you insulate your economy from global oil volatility. It reframes the electric vehicle from a symbol of environmentalism into a strategic tool for national sovereignty.
It is a profound shift, and it really highlights how interconnected this all is.
No.
A local utility denying a grid connection impacts the software needed to manage a charger, which impacts the economics of a local delivery fleet, which relies on the chemistry of an LFP battery, which ultimately ties back to global geopolitical sovereignty.
It's all connected, and if we connect all of these dots, it leaves us with a rather provocative thought for you to mull over.
Okay, let's hear it.
We've talked about the incredible cycle life of modern batteries, and we've talked about bidirectional charging, turning vehicles into mobile power plants. If an EV battery can outlast the physical chassis of the car, and it can actively generate revenue by stabilizing the local grid, How long is it until we stop buying cars primarily for mobility and start buying them primarily as personal energy trading assets that just happen to also drive us to the grocery store?
That is a wild thought to leave on. The car as a revenue-generating power plant in your garage. If you enjoyed this episode, new episodes drop every 2 weeks. Also, check out our other editions on future mobility and market evolution, next-gen vehicle intelligence, and commercial fleet insights. Thank you so much for joining us on this deep dive. Don't forget to subscribe, and we will see you next time.